Hi everybody, today we're going to go over the calculations for experiment 11.2 in Apologia Chemistry, which is the baking soda and vinegar balloon assembly. This is an experiment where you're having baking soda and vinegar in a jar and you are reacting them and catching the carbon dioxide that's produced in a balloon. So the question that we're working with today is a chemist combines 75 grams of vinegar with an unknown quantity of baking soda in a bottle and balloon assembly. This is your bottle and balloon assembly. Experiment 11.2. When the reaction is complete, the balloon has a circumference of 45.58 centimeters. So we just measure the circumference around the balloon with a tape measure. This one's smaller than that, but we're going to use these numbers. What mass of baking soda was consumed in the reaction if the temperature was 22.1 degrees Celsius and the atmospheric pressure was 0.98 atm? Okay, there's a lot in there. I'm going to tell you guys from the very beginning, you do not need all of this information to solve this problem. There's something else they threw in there that you don't need, but we're going to just write everything down anyway because I want to erase this. So it does tell you, let's see, we had 75.0 grams of vinegar. What else did we learn in here? Circumference equals 45.58 centimeters. We also learned the temperature was 22.1 degrees Celsius and the pressure, the atmospheric pressure, was 0.98 atm. Those are the things that we can glean from this. Make sense? Okay, before I erase this, the most important question, and the first question you should always ask yourself is, what am I looking for? What am I after? Because there's so many different variables that you could be trying to find in a gas equation like this. What is it we are looking for? And that's going to be kind of like our guiding compass as we work through this multi-step problem. So, and I just literally on my papers, upper right-hand corner, I write looking for and I write it out. You guys should too. Looking for, what is it asking for? What mass of baking soda was consumed in the reaction? So we are looking for mass of baking soda. All right, what are my units going to be? What units is this going to be in? It's going to be in grams. That's a good unit for mass. Okay, now I'm going to erase this so I have more space. We got the stuff out of this that we need to be able to work this problem. Okay, so the next thing I want you to think about is we're gonna strategize. We're gonna strategize our way through this problem. This problem has to do with gases. So I want you to think, what do I know about gases? Well, you do know the ideal gas law, which is a favorite among teachers. So if you're doing anything with gases in high school chemistry or college general chemistry, it is a pretty safe bet that the ideal gas law is going to be involved. So the ideal gas law is PV equals nRT. I'm going to leave that right there because we're going to be using that. Okay, so the other thing I want you to write down is what these things mean. So just because if you're in an exam, you don't want to have to be like trying to remember what all of the abbreviations stand for. Just write it out so you have it right in front of you, and then you can reference it whenever you want to. So P is pressure. V is your volume. N is your number of moles. R is a constant. It is called the ideal gas constant because it is the constant inside the ideal gas law. So R is your constant. And that one you're probably just going to look up. T is your temperature. Okay, the very first one we're going to find is the ideal gas constant because constants are really cool. You just look them up. unless your teacher tells you to memorize it, but most of the time you just look it up. And they come with units, and the units tell you the units that you need for all the other pieces. So if you cannot remember what your units of pressure or volume or temperature is supposed to be, this constant tells you. I'll show you. So in this book, it's on page 403, and R equals 0.08 what? 21. 21. And now here's the units. Get this. This is crazy. Liters, atmospheres over mole kelvins. Now that's mole times Kelvin. That's a lot, but that just tells me that my volume needs to be in liters, my pressure needs to be in atmospheres, my temperature needs to be in Kelvin, we're gonna have to do that calculation, and the number of moles is moles, obviously. So that just, even if you don't really know much about the ideal gas law, this just told you, this constant just told you how to use it. So now we just need to find all the missing pieces to solve our problem. So we are trying to find out the quantity of baking soda that was consumed. So this is the one we're going to be after right here, the number of moles. Everything else we should be able to figure out. Okay, so let's just start with the top and work our ways down. We're going to start with finding pressure. P is for pressure. Okay, now we know from our information that we were given inside of our problem that the total pressure is 0.98 atmospheres. Now, if the only gas in this balloon was carbon dioxide, that would be fine. Why is the gas inside this balloon the same pressure as the air around us? And this, by the way, you can just read this off of a barometer wherever you live. If you're close to sea level, it should be around 1 atmosphere, but it also depends on the weather. If you're higher up in the mountains, it's going to be less. Okay, so why is this equal to the pressure around us? Well, it's because if the pressure inside the balloon were less, the balloon would be shrinking down from the pressure around us. And if the pressure inside the balloon were greater, it would be expanding the balloon. Since it is no longer expanding and it's not contracting, I know that the pressure inside this balloon right now is the same as the pressure in the atmosphere. So our total pressure is 0.98 atmosphere. And that would be the answer that we would plug into this equation if the only gas in the balloon was carbon dioxide that was produced by the reaction. However, it's not, because there is also water. And so that is going to, we have to calculate that too. So when you have a pressure that's made up of multiple gases, it's pretty simple. Your total pressure, this little subscript T is just telling me what kind of pressure I'm talking about, is going to equal, the pressure in that balloon is going to equal the pressure of the carbon dioxide plus the pressure of the water vapor. Okay? And we want to find how much was just from the carbon dioxide, because that was what was given off in this reaction. All right, so you know what, maybe, okay, I'll put up the chemical reaction in just a minute, the chemical formula. Let's just find our pressures right now. So how do we know the pressure that water is contributing? Well, there is it's based on temperature, and there is a chart for that. So I want you guys to look at table 11.2. It's right here on page 397. So based on the temperature, this chart is in Celsius. You know what your water pressure is going to be. Your water vapor pressure is going to be. So we knew from the information that we were given that our temperature is 22.1 degrees Celsius. So we get to look here, we have to round to the nearest degree. That's important because you know when you're rounding, that is going to affect your significant figures. Even though we were given 3 significant figures, this chart only has 2. So we are going to, that's a key, that our answer is only going to have 2 significant figures when we're all done. Okay, so 22 degrees, we have to round at 22 degrees, and it says the vapor pressure is 19.8 torrs. So the vapor pressure of water at 22 degrees, which is what we are, equals, 19.8 torr. Now, Do we want to be dealing in torrs? No, we want to be dealing in atmospheres because the pressure, the total pressure of our surrounding is not in torrs, it's in atmospheres. Okay, so we need to change this. We change it by, there are 760 torrs in 1 atmosphere. And its units are great because they tell you how to put these up. You know you have to cancel out torrs, and if torrs is on the top here, which it is if it's not in the bottom of a fraction, then you know it has to go on the bottom over here. So we cancel our torrs out, do the division problem, and what did I get? Let's see here. I got 0.026 atmospheres. Okay, so now I know the total pressure, which was 0.98 atmospheres, equals the pressure of carbon dioxide, which I do not know yet, plus the pressure from the water vapor, which was 0.026 atm. Now, since I want to isolate this, subtract this from both sides. This is your algebra, people. Algebra is so useful. And I'm not doing math in front of you guys. Okay. And I got the answer of 0.954 atm, but you can check my work. And that is the pressure of the CO2. Okay, that's great. That's the pressure that we're going to be using in the ideal gas law. So we just found our pressure. So I'm going to go ahead and just use these same spaces. This was our pressure total. Our pressure of CO2, which we just found, is 954 atmospheres. Okay, so we just found another piece to our puzzle. We still need to find volume. We still need to find our temperature. We already have this. And then we can find our number of moles. Okay, all right, so we just did one step. We did our pressure. Next one in line is volume. So let's see. And I think it's really nice that this constant tells us volume has to be in liters. To use this gas law, you have to convert it to liters. And we were given centimeters. So we gotta go from centimeters to liters. So think about that for a second while I erase this. Okay, so let's just talk about volume in general. Okay, so this is not a perfect sphere, I get that, but we are going to estimate it as a sphere because it's pretty close. It's pretty close. Now, if you remember from your geometry that the equation of a sphere, the volume of a sphere, equals 4/3 pi r cubed. Okay? If you forget these, just look them up. Don't ever be too lazy to look something up, okay? The volume of a sphere, 4/3 pi r cubed. Okay, well we don't have r, we just have circumference. Well, we know that if we looked at this as a circle, like say you cut this balloon just like this, you'd have a circle. So now, how do we relate a circumference of a circle to its radius? Okay, so the circumference of a circle equals 2 pi r. So if we take the circumference and divide by 2 pi, we will get r, and then we can plug it into this one. So that is exactly what we're going to do. Our circumference, 45.58 centimeters divided by 2 pi equals our radius. And just use this in the calculator. That's the best way to do that. So where did I put that? Okay. Um, 7.238 centimeters. Okay, 7.238 centimeters. I'm just keeping around 4 digits because I know in the end I'm only going to need 2, and this makes sure I'm not going to have any rounding errors, because when you get out that far, it's not going to affect your answer. Okay, so now I'm going to take this radius and plug it back into this equation to get my volume. So this, again, you can do it in your calculator. 4/3. Just be careful to know that your calculator can do parentheses, or else be very strategic about how you put your numbers in. If your calculator does not have, if your calculator does not have parentheses, or you don't know how to do it, I would take this number, multiply it 3 times, 7.238 times 7.238 times 7.238 times pi, hopefully your calculator has pi, times 4, and then divided by 3. Or you can use parentheses, same thing. Okay, then this is gonna pop out your volume, which is 1,588 centimeters cubed, because we cubed this centimeters. This has centimeters and now it's centimeters cubed, which is a volume, and that's great. We also happen to know that 1 cubic centimeter is 1,000th of a liter, which is what we are after. So we're just going to divide this by 1,000, 3 zeros, put it out there, 1.588 liters. So now we just found another piece that we need. So over here in our list, we also found that this balloon produced, actually this one's a little small, it's probably bigger than that, but anyway, we're using these numbers, 1.588 liters. Okay, we just found the next piece of our puzzle. There's only one piece we need left before we can solve for moles. All right, is this? Before I do that though, I forgot, I want to put at the top the whole chemical reaction so you can see what's going on. I should have done that at the beginning, but anyway, we'll do it now. Okay, so you have your vinegar. So white vinegar is acetic acid mixed with water. So we're just gonna do, the water's not doing anything, it's just sitting there, we're gonna ignore that. C2H4O2 is a liquid, and that is your acetic acid, plus your baking soda, which is also called sodium bicarbonate, NaHCO3, which is a solid, and that will produce water, plus carbon dioxide, which is what we were measuring coming up into this balloon, plus a sodium acetate, which is the water stuff on the bottom. It's like a salt. And this is aqueous. This is a gas. This is a liquid, although we do have water vapor because it's over liquid. Okay, all right. We will need this formula later. We're gonna just leave it there for right now. Okay, next part, maybe I'll switch to black. I don't know if you can see the difference, but last part is our temperature. Now we already have our temperature, but there's a little bit of a problem. This constant tells us we need our temperature in kelvins, and we only have it in Celsius. So that's simple. You take your Celsius and you add it to 273.15, and that's your Kelvin. So let's say our temperature is 22.1 degrees Celsius. The conversion is you add 275.15. And what did we get? Yeah, I got 295.25 Kelvin. That's what I got. So that was a pretty easy, simple calculation. And now we have this part of the ideal gas law. So these are the things we were given up here, and all these things over here are the pieces of the ideal gas law that we're trying to create so that we can use this right there. That's what we want to use. Okay, so our temperature is 295.25 kelvins. Oh, I'm so excited. Okay, We have all of these pieces together. That is awesome. So now for the big calculation. PV equals nRT. N is what we're after. We want to isolate that. So let's divide both sides by RT. Okay? So we get N is going to equal P times V divided by R times T. Okay? So now let's plug these things in. Our pressure is 0.954 atm times our volume, which is 1.588 liters, divided by our constant, which is 0.0821 liters, atmospheres. Never forget your units, guys. These are important. Liters, atmospheres, mole, Kelvin, there, and our temperature, which is 295.25 Kelvin. Okay, now this is where your units just totally shine. This is wonderful because look, our liters cross off with liters. Our atmospheres cross out with atmospheres. Our Kelvin, even though it's in the denominator, this is in the denominator of the denominator. So our Kelvin crosses out. And this, when you're dividing by something, this pops back on top. There's your algebra. And the answer will be in moles. So now we multiply this times this, divided by this, and we get the answer of 0.06249 moles. I should say a mole is M-O-L-E, or moles with an S on the end, but we get really lazy sometime and the abbreviation is just M-O-L, even though it's not much of an abbreviation, just so you know. I'm not actually misspelling it. It really is legit. Okay, I am so happy. We got our answer, right? So are we done? It's so easy to get to this point and say, oh my gosh, we made it all the way to the end, we're done. But wait a minute, am I looking for moles? Let's go all the way back up here. What am I looking for in the first place? Was I looking for moles of baking soda? Actually, I was not. I'm looking for mass of baking soda, and I need to end up with something in grams. So, my friends, we are not done. Okay, but I need more space. This is where we're going to be using our chemical equation. I know how many moles of the baking soda I used, but I don't know its weight. I don't know its mass, I should say, not weight. That's improper. Okay, so can you think of anything that you use in chemistry that helps you relate grams to moles? And I hope that that you remember that immediately the periodic table comes to your mind. So grab a periodic table right here, and there's all these little numbers on the bottom, and that is how many grams per mole of that particular atom. And so we just add those all up for how many atoms we have in this molecule, and then we know how many atoms we have in a mole of that molecule. So this is going to be some adding, no problem. Okay, so let's just start from the beginning. We have one sodium atom, okay? So that means that one sodium atom is going to weigh 23 grams per mole. Then we have one hydrogen atom. Let's add that one up. 1.01 grams per mole. We have one carbon atom. No problem. 16 grams per mole. Oh, I'm sorry, that's oxygen. Sorry, 12 grams per mole. And then lastly is the oxygen. But now we have 3 of those. Don't forget that, 3. So your oxygen is an O3. You're going to have 16.0 grams per mole times 3. Okay, which is going to equal 48. Okay. Now if you add all these up, just use this in your calculator, 23 plus 1.01 plus 12 plus 48, you're going to get 84.01 grams per mole. I'm going to box that. All right, everybody see how we got that answer? All right, now we have grams per mole, and we know how many moles, so we can figure out our grams, but I need more space. I'm going to erase this equation because I need space, and we've already used it. Okay, so again, your units are your friends. You know you have this many moles, 0.6249 moles, but we don't want moles. So when you do your multiplying, you want your moles to be on the bottom so they cancel out, because we don't want moles, we want grams, right? That's what we're after. So we're gonna put the grams on top, 84.01 grams per 1 mole. That way our moles cancel out. We just do a simple multiplication, this times this, and we end up with, oh, what did we end up with? 5.249 grams. And we were after grams. That's what we were looking for. We were looking for the grams of baking soda, and we found them. So the very last step, always the very, very last step, is your significant figures. We did have to round to only 2 digits on the temperature when we were finding our atmospheric pressure of, our pressure of water vapor. So I'm going to say that we need to round to 2 significant figures. So we're going to end up with 5.2 grams as our final answer. Congratulations, guys, we did it. We found what we were looking for. Great job, everybody, and thank you so much for watching.